Welcome. I am glad to have you. We're going to walk through using perpendicular bisectors. And yes, it has a plural there, but go ahead and scrub out the S because we're looking at a perpendicular bisector of a segment. So when you hear a perpendicular bisector, I want you to think of that as of a segment. You are bisecting a segment. You always bisect a segment using a perpendicular bisector. So how do we use these perpendicular bisectors to solve problems is our essential question. And first of all, let's define a perpendicular bisector. You know what that is, but let's remind ourselves that it is a segment or ray or line or plane even that is perpendicular to a segment at its midpoint. In other words, it cuts through the midpoint. You will remember, of course, perpendicular means that it intersects at a right angle. And then bisector, bi is the prefix, meaning two. Sector, sections, you can think of it that way. So this deal, that's could be a ray, line, or even a plane, comes through and it goes through the midpoint. So label that on your notes as the capital M midpoint. And not only is it a bisector, but it's also a perpendicular bisector, meaning that it is perpendicular to that segment. So if this is the midpoint, then these two segments on the right and on the left are congruent to each other. So that's why we have congruent markings there. Perpendicular bisector. And what's really cool about this perpendicular bisector of a segment is that every single point on this perpendicular bisector is equidistant. Equidistant? What does that mean? Well, like what it sounds. Equal distance. It is equal distance from the two endpoints of that perpendicular bisector. So you can see here that here is a particular point on this perpendicular bisector, and each point here is equidistant from the endpoints of the segment. So in this particular case, point C is equidistant from these two endpoints. Therefore, the length of segment AC is equal to the length of segment CB. Or you could say that segment AC is congruent to segment CB. And that kind of makes sense, doesn't it? Because think of this as a tent. So here's your tent pole that is raising your tent, but when it's laid down on the ground, right down here, of course this is the midpoint, so obviously that is equidistant from the ends of your tent, and as you raise up the tent, then it continues to be equidistant from the endpoints. So whether it's down here or up there or way up here, it still is always going to be, as long as it's on this perpendicular bisector, it's always going to be equidistant from the endpoints. Then a converse of that theorem, remember converse means to switch, so you're thinking of this guy, poor guy, wearing Converse sneakers. He has his right sneaker on his left foot and his left sneaker on his right foot. So you're switching. So what we said here first of all is that if this is a perpendicular bisector, then every point on it is equidistant from the endpoints. Now we're going to take the converse of that and say that if a point is equidistant from the endpoints of a segment, then that point will lie on a perpendicular bisector, I guess the perpendicular bisector of that segment. So the question is, does point D lie on this perpendicular bisector? Will this perpendicular bisector intersect and go over this point? And the answer is yes, it will. How do we know that? Because this point is equidistant from the ends of this segment, and therefore, according to this converse of the perpendicular bisector theorem, we know it will be on the perpendicular bisector. So let's look at some examples. Are you ready? Example number 1. We are told that line BD, here's line BD, is the perpendicular, so it's that's a definite article, so there's only one perpendicular bisector, so it is the perpendicular bisector of segment AC. So here is segment AC, and when we are told that this is the perpendicular bisector, that tells us all kinds of information. We know, first of all, that it's perpendicular to this segment CA. We also know that it is a bisector of, therefore this is the midpoint of this segment, and therefore this upper segment CB is congruent to this lower segment BA. And what else do we know? We also know that every single point on this perpendicular bisector is equidistant from the endpoints of the segment. So in other words, these segments here are congruent with each other. And so could I just put one single tick marks there? No, don't do that, because that would be saying that these two segments are also congruent. So therefore let me use double tick marks on these. So these two segments are congruent to each other, and these two segments are congruent to each other. And as you know, if two segments are congruent, then they have the same length, and so therefore I can set 5x equal to 3x plus 14, and there's my equation. With these kinds of problems, when you're solving for x, or solving for the length of something or the measure of an angle, take two expressions, or maybe sometimes three or four, but try to relate them to each other in an equation. And so that's what we've done here. 5x equals 3x plus 14, and we simply solve this for x by subtracting 3x from both sides and then dividing both sides by 2, and that gives us x equals 7. So is that our answer? Wait a second. They're asking us to find AD. Now, when it has a bar on top of it, that means segment AD. And of course, if it had one arrow, that'd mean a ray. If it had two arrows, it'd mean a line. But what's up with that? What if it just has the two letters? What does that mean in geometry? It means the length of segment AD. So here is segment AD. So I know what x is. Now what I do is substitute that in into this expression for x. And you know that the operation between the 5 and the x is multiplication. So 5 times 7 gives me 35. So the length of AD, segment AD, is 35. And what do you think, if I was to plug in x equals 7 into this expression, what do you think I would get? Well, I better get the same thing, right? Because these two segments should be congruent, because this point is on the perpendicular bisector, and each point on the perpendicular bisector is equidistant from the endpoints. Let's go ahead and try that. Put 7 in there. 3 times 7 is 21. 21 plus 14, yep, that's 35. That works. Pretty cool. Here we go, another example for us, and we are told that in this diagram, this line WX is the perpendicular bisector of segment YZ. And so they're asking us the question, what segment lengths in the diagram are equal? Well, if this is a perpendicular bisector, you know that these two segments here are congruent, and therefore the lengths are equal, because this is the midpoint. A bisector goes through the midpoint. And because this is a perpendicular bisector, each point on this perpendicular bisector is equidistant from the endpoints of your segment. Therefore, these two segments are congruent with each other. And also, of course, we're told that these two segments are both 25, so those two segments are also congruent to each other. So notice how I put single tick marks on this pair, double tick marks on this pair, and triple tick marks on that one. Of course, I could have done it differently. I could have said triple tick marks down here, but you get the point. So now the question is V, what is V? Well, V is a point. Is V on line WX? Here is line WX. So when line WX cooks along through here, is it going to go through point V? And the answer is yes, because of what? Oh, because this is a perpendicular bisector, and this point V is equidistant from the endpoints, and therefore, and we know that each point on the perpendicular bisector is equidistant from the endpoints. Have I said that enough times? Now, I can say it all I want to, but you need to say it. You need to practice this in order for you to understand it, right? Recognizing the right answer when told is not our objective here. You listening to a video is not our goal. You need to think about this. So pause this video. You bum, don't just ride through this this video and write down what I write down. Slow down and think about it. I don't mean to insult you, but I have so many students that are just writing things down and not thinking. So if you are thinking, thank you for doing that. Pause the video and do this problem on your own. Okay, let's jump into concurrency. Here is another concept that we will use a number of times in geometry. We're going to introduce it here. Concurrency. Not currency. Currency is money. Concurrency is a different concept in geometry, at least. When three or more lines, rays, or segments intersect in the same point, they are called concurrent lines, or rays or segments. And the point of intersection of those lines, rays, or segments is called the point of concurrency. Okay, so here are three lines. Are these three lines concurrent? Well, no, they're not, because they do not intersect at the same point. Now they are concurrent because all 3 points are intersecting, all 3 segments are intersecting at one point, and this is, right there, is the point of concurrency. It is that point at which all 3 of these segments, or lines, or whatever you want to call them, are intersecting. So, what's fascinating about perpendicular bisectors of a triangle is that these perpendicular bisectors of a triangle are concurrent, and the point of concurrency of the perpendicular bisector is the circumcenter of the triangle. That is, it is the center of a circle that circumscribes the triangle. That's a lot that I just said there. Let me back up, slow down, and describe to you what I'm saying. The perpendicular bisector of a triangle, perpendicular bisectors, plural, of a triangle intersect at a point that is equidistant from the vertices of the triangle. Okay, that makes sense, doesn't it? Let's look at this one here. So think of this, ignore the fact that this is in a triangle, and here is a segment, and this is the perpendicular bisector of that segment. So this is the midpoint of this side, and it's perpendicular. So you remember that each point on this perpendicular bisector is equidistant from the endpoints of that segment. Okay, so we got that. Now let's kind of rotate this guy around. In fact, let's go and do this one. It's a little bit bigger, easier to see. So here is another perpendicular bisector of this other side, and each point on this perpendicular bisector is equidistant from the endpoints of this point, or this segment. Okay. Now notice that these two perpendicular bisectors intersect. Now remember, this point is equidistant from these two endpoints, right? In other words, these two segments are congruent to each other. But that's also true over here, that for this perpendicular bisector at this particular point, it's the same segment there that we were talking about for this other one, right? And so all 3 of these lengths, these segments here, are congruent to each other. In other words, this point is equidistant from these two vertices. Remember, this is a vertex on this triangle, and here's another vertex. So this point is equidistant from these two vertices. At this point here, it is also equidistant from these two endpoints of the well, these two vertices. And then, interestingly, fascinatingly, this perpendicular bisector also intersects at the same exact point. It will always be that way for a triangle. This triangle kind of looks like it's a equilateral triangle. It is not. Well, let me say it this way. No, it is not. It is not. It definitely is not. So the point is that the point of concurrence, or say it this way, the perpendicular bisectors will always be concurrent in a triangle, regardless of whether it is a acute triangle, like you see here, or a right triangle, as you see here, or an obtuse triangle, as you see here. And interestingly, in an acute triangle, the point of concurrence, oops, can you see that? The point of concurrence is inside of the triangle. With a right triangle, the point of concurrency, which we are calling the circumcenter, okay, the point of concurrency where these three perpendicular bisectors intersect, we are calling that the circumcenter. That's a unique kind of point of concurrency. It's the point of concurrency of these perpendicular bisectors, and we call that the circumcenter. The circumcenter, let's back it up again. The circumcenter for an acute triangle is inside of the triangle. The circumcenter for a right triangle, it turns out, will always be on the hypotenuse. So include there on the hypotenuse in your notes. And the circumcenter for an obtuse triangle is always outside of the triangle. So what's this thing about it being the circumcenter and the center of a circle that circumscribes the triangle? What does this circumscribe? Well, remember, this point here, let's go back to what we have here. So here's your perpendicular bisector. It's equidistant from the endpoints of this segment. So these two segments are congruent to each other. And then same thing over here. So these are radii. We can think of them as radii of a circle that circumscribes. Circumscribes means to go around. If you were to circumscribe the globe, you would go around the globe. So this circle circumscribes. It goes, and of course my art history work here is lousy, and I probably should have redone it, but it should kind of dip down here farther so that it's always this distance from the center, and of course it should go through this this vertex there. So ignore my sloppy circle. You make a better circle than I can. You can do that. But notice the circle goes through each of these vertices and is centered at the circumcenter. Notice when I have an acute triangle, the circle goes through, when the circle goes through these vertices, now your circumcenter is in the triangle. But with a right triangle, this hypotenuse actually turns into a diameter. See how your circumcenter is on the hypotenuse, and therefore the circumcenter will always be the midpoint of that hypotenuse, and the hypotenuse will always be a diameter of the circle. Very interesting. And when you have an obtuse, so this angle is greater than 90 and less than 180, then your circumcenter is outside, because in order to get a circle going through each of these three vertices, the circle has to come up way above here, so it draws your center outside of that triangle. Isn't that amazing? I know you're just thrilled by that. So why is this useful? Well, for example, if you were doing some city planning and you wanted, or say you were not city planning, but you were a supplier for these three. Where's the third one? Over here. These three different, what do they call them? Snack carts, and you wanted to be equidistant, so it's the same distance from your little supply shed to your snack carts, assuming that there's roads. Maybe you have a drone. There it is. You have a drone and you fly it. Zzz, you fly it out to your cart. Okay, so you want it to be equidistant. So how do you figure out where the point is that is equidistant from each of these three carts? Well, what you do is you make a triangle with these carts at the vertices of that triangle. In other words, this image down here is your triangle, and you draw your side between those two snack carts. You find your perpendicular bisector of that side, and then you do the same thing for each of the other sides, and those perpendicular bisectors are concurrent. This is the point of concurrency of these perpendicular bisectors, which we call the circumcenter. And why is that? Because this point is equidistant from the vertices. And like we did before, maybe I can do a better circle. Probably not. Here's my great example. Oh, yeah, there it is. Almost perfect, huh? If you look at it, if you squint at it with one eye and then hold a hand over that eye that's open, it looks like a circle. Sorry about that, not too beautiful. But you get the point, that we have now found the circumcenter of this triangle, which is equidistant from each of these vertices. Okay, hope that's helpful to you, and may the Lord bless you, and I look forward to seeing you in class.